In this video, I'm going to cover component independence. So I'm going to start with talking about the characteristics of a good design. The high quality design should have the following characteristics that lead to quality products. You have to be easy to understand, easy to implement, easy to test, easy to modify, and it has to translate directly from the requirement spec. Modifiability is especially important since changes to requirements or changes for fault correction sometimes result in a design change. And you usually talk about design for change when you're talking about that modifiability. So that brings me to what this video is about. In order to satisfy a good design, you usually have to have lots of independence between the different components that you're going to be designing in your design document. That's because it makes it easier to understand how a component works if it's not really tied closely to another one. Because the more two things are tied together, then you have to understand both in order to kind of comprehend what each one is about. It's also much easier to modify something that's working independent. If something is highly dependent on something else, then one modification of one necessitates that you have to go and change the other thing. The last reason you want to do this is because it helps to isolate and fix the causes of system failure, which can be traced back from code back to the design. So that being said, there are two main based on the characteristics of a good design. There are the degree of the component independence can be measured in two ways. You can measure the degree of coupling and you can measure the degree of cohesion. So first let's talk about coupling. There is actually a space between highly coupled devices to uncoupled devices. For a highly coupled device, there's a great deal of independence between the different components. For uncoupled devices, on the other hand, the components have no interconnections at all and they are completely independent. So here this diagram is actually kind of illustrating that. So where you imagine each one of the green rectangles are a specific component, you notice there are a lot more arrows which shows you have flows between them. A highly coupled one means that there are lots of dependencies there. So here is the spectrum of types of coupling from high to low coupling. High coupling is bad because that means there are a lot of independence, whereas low coupling is good because the system can become to the point where modules don't depend on one another. So I'm going to do this discussion going down this diagram from content coupling down to uncoupled. So the first type of coupling is content coupling, and that's the worst kind, where one component actually modifies another, and the modified component is completely dependent on the modifying one. It may occur when one component modifies internal data item in another component, or when one component branches in the middle of another component. So here's an example where we have component A which uses component B and C, but component B actually content couples with component D. And so a lot of the times this happens when you use go-to statements. So imagine you're writing one routine called routine B, and in the middle of that routine you have a go-to statement that goes to another routine which is routine D, and then going to perform some sort of code in routine D, and then probably branch back with another go-to back to routine B. This means that if for some reason a designer decided to go and change component D, component B's operation would change drastically because B no longer has control over that change. Go-tos used in this way are usually a very, very bad idea, and is the worst form of coupling that you're going to encounter. The next level down is common coupling. This occurs when data is accessible from a common data store. So dependency exists since making a change to the common data means you have to trace it back to all the components that access that single piece of data, and then you have to evaluate the effect of the change. And a lot of the times it's difficult to determine which component is responsible for having having to set a variable to a particular value. So here we have example of common coupling. You have the global variables in one place, in one central data store, and then component X is trying to change v1 to 0, whereas component Y is incrementing v1, and component Z is also modifying v1. So all three components are actually modifying the same variable in some way, and then depending on who runs first or how fast they're running and that kind of thing, sometimes you can get tripped up very easily. So again, this is not always the best way to do it. A lot of the time, this is why people say don't really, you try to minimize the global variables as much as possible, because it's a lot harder sometimes to track which components are modifying it at any point in time, and when software becomes large, it's very hard to trace. The next level down is control coupling. This occurs when one component passes parameters to control the activity of another component. It's impossible for the control component to function without direction from the controlling one. The way to mitigate against this is to have each component perform only one function or execute only one process. That means you minimize the passing of the control information as much as possible. Finally, this brings us to two of the lower forms of coupling, which is a lot more preferable. In stamp coupling, you're passing data structures between one component and another, and the data structure itself is passed. This means that the data values, format, and organization must be matched between the interacting components. So they have to know how we're going to format the data, and they have to agree on that upfront, which is usually not that bad. Data coupling is probably the type that you really want, and it occurs when data is passed from one component to another. It's simpler than stamp coupling and leaves less room for error. It's the most desirable form of coupling, and it's the easiest to trace data and make changes. So if you have to couple, data coupling is the one you probably want. Stamp coupling is not so bad, especially when it's used in object-oriented design, and you actually have transactional processes based on the data structures. But in general, these low amounts of coupling are the ones you want. The only thing lower than this is if you have an uncoupled system, and idea is no coupling. So the next idea that you have to understand about independence of components is cohesion, which is sort of the internal glue, which is the interdependence with which a component is constructed. The more cohesive a component, the more related are the internal parts of the component to each other and to its overall purpose. So in other words, the component is cohesive if all elements of the component are directed toward and are essential for performing the same task. So here's the spectrum between a highly cohesive component to one with low cohesion. Now, cohesion on the other hand, you want high cohesion. High cohesion is good. Low cohesion is bad. So I'm going to start from the bottom of this arrow and work my way upward from low and the undesirable types of cohesion to something that's more desirable. So the lowest form of cohesion is coincidental, and it's the worst degree, where you go and you group all of the parts of the component, and all those groups are unrelated to one another, which is where the name comes from. It's just by coincidence we happen to just put all these functions together. These parts are just placed there for reasons of convenience. There's just no real reason for them to be related there. The next level up, though still not desirable, is logical cohesion, where you group functions together based on logic, based on similarity of the function that they perform. So one component may read all kinds of input regardless of where the input is coming from or where it will be used. So perhaps in a power flow analysis problem, we group all of the functions that add things, where one is just adding some random complex numbers, one is adding two matrices on a bus, one is adding, I don't know, there's some regular old-fashioned point values, but because all of these things are doing addition, we just group them together because, well, they're performing the same kind of function, even though they're performing the same kind of function in different application areas. The next level up is temporal cohesion, where you group your functions based on performing it in some sort of sequence, where the sequence is only related by time and time alone. So this function performs at time step, at the first time step, and then this function performs at the next time step, and so on, and so forth. And you group them together because they're only related by the fact that they happen in terms of time. The next one sounds a lot like it, but it's about procedural. It's procedural cohesion, where it's not just about time, but the functions themselves have to be performed in a certain order, and perhaps the data coming into the function below is needed by the one that's processing it before. Slightly better than temporal cohesion, but still not that desirable. The next level up for the next level up the cohesion ladder is communicational cohesion, where you associate functions because they operate on or produce the same data set. So you might have unrelated data that's fetched together because the fetch can be done with only one disk or tape access. This is a very old school example. This destroys modularity and functional independence of design. Getting to a more high level of cohesion is sequential cohesion. The output from one part of a component is input into the next part of the component. It's possible that the component will not contain all of the processing related to a function. So now we're actually passing data from one to the next. Finally, this is the highest level of cohesion that you can have, which is functional cohesion, where every processing element is essential to performance of a single function, and all elements contained in one component, and it performs only that function for which it was designed. So I'm going to close on the note for control issues. When you're decomposing your design, and you're talking about all of these types of control, all these types of modules, one thing that you want to look at is how many components have control over another. We have two metrics. You have fan in and fan out. So fan in is the number of components controlling a particular component, and fan out is the number of components controlled by a component. So here's a quick example. Here we note that for component A in system 1 has a fan out of 3 and a fan in of 0. B has a fan in of 1 and a fan out of 1. In system 2, A has a fan out of 5 and a fan in of 0. So you see, by listing the fan in and fan out for a particular component, we have an idea of the amount of independence of that component as well. So that does it for this video. Thanks for listening. Bye.